Hello and welcome to the next talk for the Science Month, which is organized in collaboration with Aisha's Kolkata Science Club and Aisha Kolkata Campus Radio. This is a science conference entirely organized by students and is for students. And today we have a really distinguished scientist with us who would be introduced by Surajit Manna, who is a third year undergraduate student majoring in chemical sciences. So over to you, Surajit, after which we'll hear this interesting talk from Dr. Aisha.
Okay, good evening to everyone attending the session, and of course, yeah, good afternoon to Dr. Bismillah. So, Dr. Aisha Bismillah obtained her MChem degree from the University of Central Lancashire before completing her PhD degree at the University of Durham in 2019, focusing on fluxional carbon cages and their shape-shifting properties. She is a recipient of the prestigious US-UK Fulbright Scholarship and had been a postdoctoral research associate in the Abrahamian Group at Dartmouth College, USA. She is currently working as a Leverhulme Research Fellow at Durham University. She was a finalist for European Young Chemist Award 2020 and was also awarded the International CAS Future Leaders Award in 2019. So I will pass the mic on to Dr. Bismillah, who will give her talk, and I hope you will enjoy the talk. Over to her.
Hi, can everyone hear me?
Yes, we
Yeah,
can
you're
hear you.
audible.
Yeah.
Perfect, thank you. So hello and good evening. My name is Aisha Bismillah, and I'm currently a Leverhulme Fellow at Durham University, working in the McGonagall Research Group. It's great to be here today. I'm really excited to talk about the research that I conducted during my PhD at Durham University, which focused on controlling crystallization and chirality within shapeshifting molecules. So just to let you know, I'm going to be starting off with the basics here. So the connectivity of molecules is generally fixed, whereas the conformation of molecules is generally dynamic. These are normally two separate entities which makes molecules easy to understand, but in some ways can also be quite restrictive. But what if you could combine conformation and connectivity to make a dynamic molecule? Well, this is what shape-shifting molecules are. These are molecules that can change their shape in a similar manner to which a Rubik's Cube moves, creating multiple configurations without ever being pulled apart. These molecules have the potential to have great significance in applications like drug discovery, as well as the regulation of protein behavior where a specific lock and key interaction is necessary. Chemists are pouring an enormous amount of effort and research time into this. They normally synthesize hundreds, if not thousands, of molecules and then test them individually to find a specific response with a protein. So essentially, we test thousands of keys that will only ever fit into one lock. We are looking to revolutionize this process by having just one molecule that can change its shape and adapt to fit into a target protein. And the molecules that we want to do this with are called shape-shifting molecules. So, boulvalene and the barbaryl cation are one of the best examples of shape-shifting molecules. These can fluctuate between thousands of structures which arise from low-energy sigmatropic rearrangements. So essentially, every carbon can exchange with every other carbon. So why are we then interested in these molecules? Why are we important? Why should you care? Well, number one, they are central to the understanding of valence isomerism. Number two, they have the potential to adapt their structures in response to our environments. And number three, they are part of a systems chemistry which is relatively unexplored. Geoffrey Bode has taken advantage of these systems by creating boronic acid substituted boulvalenes, which allow for covalent and non-covalent binding to a large number of analytes. the way in which this works is that each analyte creates a characteristic shift in the equilibrium distribution of the Bulveline isomers. So although this is a step in the right direction, these systems are actually quite complicated, and it's because there's due to the large number of isomers. And at the moment, we don't have much understanding of how they change in response to their environment, and more importantly, how we can control it. We need to build a fundamental understanding if we're going to implement these compounds for purposes like protein binding. Barbarylane is a much simpler shape-shifting molecule. It only converts between two structures. Therefore, it's actually quite tractable and a better subject to study in order to establish a fundamental understanding of how these molecules adapt in different environments. And this will actually allow us to move closer towards our long-term goals. So, my contribution to this area and the goals of some of my research projects have been to utilize barbarylane to not only tackle the issues of complexity that we see in other shape-shifting molecules, but to determine, one, if we can get a quantitative understanding of how these molecules change in different environments, and two, then take advantage of the dynamics and harness them in a way where we can take control for the functions that we need. So the first way that I've gone about this, and the first project I'm going to talk about today, is functionalization of the barbarylane, which has allowed us to look at how the shape changes when you move from the solution state to the solid state. So we have a change in the environment, and this is actually important for biological systems. This study allowed us to gain a fundamental understanding of how these systems behave when the environment is changed, and also allowed us to determine what techniques we can use to probe it. One of the other projects in my PhD then looked to control the dynamics and shapes of the shape-shifting molecules, and we chose to do this through chirality, as again, this is important when interacting with biological systems, and we did this in either covalent fashion through the addition of a chiral tether, or in a non-covalent manner by adding a biological macrocyclic host, such as beta-cyclodextrin. So, the first thing that we did was synthesize a small library of some simple systems where the R group varies between a methoxy group, a fluorine, and a hydrogen atom. Something that I'd like to point out here is that the two barbarylanes, 1 and 1', even though they look exactly the same, there is a difference between them. So in structure 1, the 3-membered cyclopropyl ring is on the right-hand side, whereas in structure 1', the 3-membered cyclopropyl ring is on the left-hand side. I'm not going to delve into this too deeply, but the key points to take away is that it's only a 3-step synthesis, relatively easy with yields that are above 80% and above. So we start off with an alkyne group, which is converted into an alkanyl cycloheptatriene. That's then converted into barbarylone through a gold catalyzed cycloisomerization, proceeding through a barbarylyl cation intermediate, which is oxidized in situ by diphenyl sulfoxide. And after a simple Grignard reagent, we get the barbarylanes ranging in yields from 58 to 75%. Looking at the proton NMR, what you can see and what we have been able to determine is that there are two structures, so 1 and 1', which are in equilibrium with one another. And this equilibrium is rapid at room temperature. And the way that these two molecules interconvert is through a simple Koch rearrangement. So if we look at the chemical shifts, what we can see is that they are a weighted average of both of these structures. And this tells us that the equilibrium constant is not equal to 1. So for a fluxional system, which is rapidly going back and forth between the two structures that you see, so 1 and 1', you would only expect to see one set of peaks in the NMR spectrum because both of the structures would lie in equilibrium with one another. And in our NMR spectrum, we do only see one set of peaks, so we can confidently say that the two structures are dynamic in the solution state. We then decided to delve a little deeper and we did some DFT calculations. We have been able to calculate the chemical shift of every single carbon within 1A and every single carbon within 1A prime. If we take the carbon labeled as 6 in 1A, this is an alkene, we see that the calculated chemical shift is 132.5 ppm. If we then turn our attention to 1A prime, where the same position is labeled as 8' and it's not an alkene, but a cyclopropyl ring, we see that the chemical shift is 33.9 ppm. So when we compared these calculated chemical shifts against the experimental value, which is 111.9 ppm, we see that the experimental value is closer to the alkene and not the cyclopropyl ring. So we can be confident that 1A is the major solution state isomer and 1A prime is the minor solution state isomer. If you lower the temperature of a fluxional system and get cold enough, you would normally expect peaks to split into the two differing structures. We would expect to have two sets of peaks, one from the structure 1b and one from the structure 1b prime. But when we lower the temperature and we go as low as 149 Kelvin here, we don't see any peak split. And this shows us that even at low temperatures, there is an equilibrium. Interestingly, we do see the peaks relating to the Barber-Lane core shift. If we look at the peak labeled 6/8 prime, as we go down in temperature, we see that it shifts downfield, and this is because it's becoming more of an alkene and less of a cyclopropyl ring. So even at low temperatures out of the two structures, isomer 1b is the major solution state isomer, therefore 1b prime is the minor solution state isomer. We also see, as we get down to 165 Kelvin, that the peaks start to broaden into the baseline, and this shows us that we have a very low energy barrier. So if we know that in the solution state, there's always one major isomer, when we go crystals of the mixture, we would expect to get the major isomer. And that is what we did see, but only for 3 of the family of 5 that we synthesized. So what about the other 2? Well, the solid state structures show that the minor isomer has selectively crystallized out. This is extremely unusual, as this is not what you would expect to see, as this is actually the higher energy isomer. So the question we need to answer now is, why is this minor isomer crystallizing out? Could it be due to these molecules being fluxional in the solid state? And something that I'd like to point out is that all the crystals were resolved to single isomers, no solvent was present, and there were no polymorphs. So we attempted to grow these crystal structures many, many times, and every single time, under different conditions and whatnot, we always got the same results here. So looking in depth at the crystal structures, we did Hirschfeld calculations, and we don't see any hydrogen bonding or any non-covalent interactions which dictate the packing. So if you look at the red spots here, those are the closest contacts to a neighboring molecule, and what these contacts are just van der Waals, so there's nothing major going on right now. We also calculated the electrostatic potential maps, and this helps us confirm our hypothesis. The heteroatoms are the most polarized areas of the structures, and this would be expected, and that the aromatic surfaces are only mildly polarized. There is absolutely no indication that this mild polarization gives rise to any atomic interactions within the solid state. So if we take a closer look at the solid state superstructures of the major and minor solution phase isomer, and take a look at the density, we see that the density is larger for the minor isomer, and this means that the crystal structure is more tightly packed. So for the minor isomer, it's packed in a head-to-tail manner, whereas the major isomer's density is lower at 1.33, and this is packed in a head-to-head manner, which actually ends up taking more space. So this means that the crystal structure of the minor isomer is driven by its shape. So it will change from the major isomer in the solution state to the minor isomer in the solid state, just so it can get better packing. To further prove our theory of shape-selective crystallization, all the Barber lanes actually form a V shape, and if you measure the angle between the two phenyl rings, we see that for the minor isomer, the angle is much smaller. So it's actually 41.6 in comparison to the major isomer, which is 67.7, and this is because of the smaller steric size of the fluorine or hydrogen atoms. This quantitative analysis proves that the dynamic preferential crystallization is driven by a preference of shape and size and not any form of any non-covalent interactions. So through this work, we have gained a fundamental understanding of how shape-shifting molecules respond dynamically through changing their shape and size when transitioning between different environments. And in this case, we looked at moving from the solution state to the solid state. Following on from this, we next looked at how Barber lanes change their chirality when placed within different chiral environments. So ever since the realization that chirality is present in most biological systems and vital to applications such as drug discovery, amongst others, chemists have been paying a lot of attention in trying to set and control it. The most common source of chirality is a carbon sp3 stereocenter, and these generally possess fixed chirality. But when we appropriately substitute our barbarylane molecules, what we get is dynamic stereochemistry of a carbon sp3 stereocenter, and this is extremely rare. We wanted to see if we could bias the stereocenter, so in other words, control it, and we did this in two different ways. The first through covalent interactions by adding a chiral tether, and secondly through non-covalent bonding interactions with a biological host, and we chose beta cyclodextrin. So to the barbarylane core, we added a chiral group. We first chose the chiral Mosher's acid chloride. To make compounds 3 and 4, we took the corresponding Mosher's acids in the presence of oxalide chloride and catalytic DMF. Acids are then converted into the acid chlorides, and then it's a simple esterification reaction where the yields are 58 and 79%. We also made another set of barbarylanes, this time starting from barbarylone instead of barbarylol. Compounds 5 and 6 are formed through a Borch reductive amination using phenylamine with sodium cyanoborohydride and mildly acidic conditions. When you add a chiral group, you get a pair of diastereoisomers which are rapidly converting. So as we have seen before, the NMR at room temperature is an average of the two structures. So barbarylone, so number 7, is an achiral molecule, a result of an internal mirror plane which is in the plane of the carbonyl bridge. We can also imagine another orthogonal mirror plane, and this is induced by the rapid dynamics of the barbarylane core. Due to this induced mirror plane, the exchange of the cyclopropane and olefinic environments play as a broad singlet. So this is the peak as labeled as 2, 4, 6, and 8. And this is one peak. When we add a stereogenic center at position 9 of the barbarylane, so then looking at compound 2, we get 2 valence enantiomers and the internal mirror plane is removed. The removal of this mirror plane allows the barbarylane core to be desymmetrized. So therefore, we now get 2 inequivalent peaks for the cyclopropane and olefinic environments. So the peak that's labeled as the broad peak labeled as 2, 4, 6, and 8 then splits into 2 peaks, one labeled as 6 and 8 and the other one labeled as 2 and 4. Then when we add a chiral tether, and we're going to take the Mosher's ester here, we remove the final induced mirror plane and we entirely desymmetrize the core. So then every proton has its own unique chemical environment. So then if we move from compound 2 to compound 4, in spectra, the middle spectra, we have 6 and 8 and 2 and 4 as 2 peaks. In the spectra below, we have 4 single peaks, which are 6, 8, 2, and 4. So comparing these spectra, we can say that the addition of a chiral tether does influence the barbarylane core. Running circular dichroism spectroscopy on the barbarylanes bearing chiral tethers show equal and opposite Cotton effects, confirming that the species synthesized are enantiomeric. To show that we can gain covalent control of these molecules in the solution state, we then compare the simulated spectra of the 3,3R diastereoisomer to the solid state NMR as well as the solution state NMR at 149 Kelvin. And what we see is that the spectra are all identical and that the peaks match up. And this is what you would expect to see if you had the same species in the solution solid state. The fact that we have the same species shows and confirms that the 3,3R diastereoisomer is the preferred one out of the 3,3R and the 3,3RS. So we can confidently say that we can control the carbon sp3 stereocenter in the solution state through the addition of a covalent tether. To best show control in the solid state is to obtain crystal structures. We were able to obtain them for both the Mosher's esters, and what they show is dynamic preferential crystallization, so i.e. just one diastereoisomer from each pair of fluxional carbon cages crystallizes out, and it's always the thermodynamically favored diastereoisomer that we get. So when we add an R Mosher's ester, we get the R barbarylane core, which is also what we see in the solution state and vice versa with the S Mosher's ester. Barbarylane 5, functionalized with a chiral amine, also crystallize out as a thermodynamically favored diastereoisomer. So if you add an R phenyl amine group, we get an S barbirylane core. So from looking at the experimental data, when we attach a covalently a chiral tether to the barbirylane core, we see that the carbon sp3 stereocenter of the barbirylane adapts its chirality. In order to impart non-covalent control over the carbon sp3 stereocenter, we chose chiral cyclodextrins, as these are biological macrocycles. Therefore, every study must be done in water, and we are getting that one step closer to mimicking the environments required for protein binding. We added the barbirol to either the chiral alpha, beta, or gamma cyclodextrins, and we see that the strongest binding occurs with beta cyclodextrin. We know this because when we look at the stack of NMRs, the biggest change in the chemical shifts occur with the beta cyclodextrin and not the alpha or gamma cyclodextrin. At the same time, upon encapsulation with the chiral beta cyclodextrin host, we also see that the remaining mirror plane is removed, allowing the barbirylane to become desymmetrized entirely. So we see 4 inequivalent peaks here. So in the third spectra down, we see 4 inequivalent peaks once the barbirol is added to the cyclodextrin. Whereas with the gamma cyclodextrin, we only see 3 peaks, so that's the bottom spectra. And when we have alpha cyclodextrin, there doesn't seem too much of a change. The data shows that there is substantial evidence that the barbirylane molecules feel the presence of the chiral environment provided by the cyclodextrin. So after choosing the chiral beta cyclodextrin and adding it to our shape-shifting molecule, we observe a binding interaction, which is evidenced by the NMR resonances corresponding to the barbirylane core shifting downfield. We're able to quantify this interaction and get an association constant of 780. After establishing that is an interaction when you add a chiral beta cyclodextrin, we move from the solution state to the solid state. What we see when looking at the solid state structure of the host-guest complex is that only the S enantiomer is nestled tightly within the cavity. Therefore, in a non-covalent manner, we demonstrate that the shape-shifting molecule has adapted its shape in order to fit inside a biological oligosaccharide. Now that we have gained a full understanding over shape-shifting molecules by looking at their shapes and structures when moving to and from the solution state to the solid state, we've been able to gain a full control over a rare carbon sp3 stereocenter in a covalent and, more importantly, in a non-covalent manner using a biological host. So where does that leave us currently? Well, we are excited for the next steps, which will involve taking what we have learned and pursuing shape-shifting molecules with proteins. I would like to thank my supervisor, Paul McGonigal, all the past and present members of the McGonigal Group, as well as the analytical services at Durham University, the funding agencies, and all of you for your attention. I'm more than happy to answer any questions. Thank you.
It was a really interesting talk, and everyone is free to ask any questions if they have. I will relay the questions.
Okay, thank you.
Meanwhile, I would like to ask a question of my own. So, you, your research found out that during crystallization, the one with the better packing shifts towards itself, right? Like the dynamic isomerism shifts towards the structure that has better packing, right?
Yes.
So, um, so can you control it in such a way that the lesser stable can, like the lesser stable structure can be like crystallized in some form? And I
Yeah.
mean,
So the whole what we're showing here is that we can control whether we get one isomer or the other isomer. It just depends on the substituent that you have. So if you have a fluorine or a hydrogen, like a small group, then you can get one isomer. Whereas if you have a bigger group, then you'll get the other isomer. So yeah, we're showing that we can control it.
and another question I would like to ask is that you said that you chose a simple system like Barbarillin because it has a few dynamic structures. So, like, does it make it like too much difficult to control for other dynamic molecules? I mean, fluxional molecules which have like thousands of structures. I mean, how will you choose a specific set of
So
structures?
So realistically, if we want to do protein binding, we will have to use the more complicated structures like bovalene. The reason we picked barbarylene now and we did studies with it is because the other systems are very complicated. So it's better to use simpler systems to get a fundamental understanding. It makes sense to do that. And then now we've got a fundamental understanding. We know how to analyze these molecules. We know we need solid state. We know we need crystals. We know we need variable temperature NMR. We can now use the more complicated systems. So we are actually working towards using them, but it will be slightly different and more complicated. So there'll probably be a lot of more DFT and stuff involved, but we just use these systems to get a fundamental understanding. But for the applications we're looking for, like protein binding, we will have to use the more complicated systems because they can change their shape more. Whereas barbalanes only change between two structures, the other ones can change between hundreds and thousands, and that is the property that we need.
Okay, thank you for the answer. And okay, so we have questions. So Sanjay is asking, can this molecule be force proteins into otherwise unstable conformations and study them, working as some kind of molecular motors?
I actually personally think they could be used as molecular motors. That is something that probably will be pursued, like adding them with switches and whatnot. And in terms of, for example, if you have something a bit more complicated, let's just say there are like 5 transition states. It's normally going between 2, but I think when we have more substitutions, then we should be able to access other transition states. But then it's just a case of how stable are they and will we be able to reach them. So I think it would be difficult, but at low temperatures, there is a chance that we will be able to see them. And then depending on the substituent that we have, for example, if we have something electron donating, then there's a chance as well. So I think we should be able to see if there are other ones that, transition states, especially when bovalene will have more transition states. Like we will be able to see them. It's just a case of picking the right molecule, picking the right temperature and conditions, and picking the right substitution.
Uh, Thank you for the answer. So Rohan says, thank you for the beautiful presentation. Can you please enlighten upon why S isomer is predominantly covalently bonding? Is it just an observation like how it fits biological system?
So at the moment, we can't say, like, for example, why it is the S isomer. Sorry, one sec. Like, why it is the S isomer that was chosen. We know that it selectively picks one. It's most likely due to the non-covalent interactions. It prefers this isomer rather than the other isomer. It probably fits better. But something that we're showing is that it's probably preferenced in the solution state as well. There's some final experiments going on to prove that, you know, it's also preferred. In terms of a reason why, it's probably due to its shape and size that this fits better in comparison to the R molecule. That's what we can say. Like, that's what we're leaning towards.
Okay. Thank you for the clarification. Another question from my side would be like there are many other examples of fluxional molecules, right? So why did you choose carbon cages? I mean, do they have some kind of special properties that interested you?
So there are other molecules that are functional, but I think we picked carbon cages, and these are only a few that I've shown here. So I showed bulvaline, the barbaryl cation, barbarylane, diazobulvaline. There are many. I think the plan is eventually to move out into all of them, because all of them have their different properties and can do different things. So that is something we'll look into. But we like these molecules and we picked them because they were studied in like the 1950s, like for a small amount of period of time, and then they got left behind. And now as chemistry has progressed, no one has, like, you know, we could use them in polymers, we could use them in liquid crystals, we could use them as motors. There's lots of things that can be done. And they're small, they're easy to make. So we think like they have properties that other molecules don't, which is being dynamic. I mean, there are some out there, but I think these ones are a different type, so it'd be worth pursuing them. And they haven't really been looked at in the sense of supramolecular chemistry before, which is what we're doing.
It's really fascinating, like how a neglected area of chemistry is like refurbished and again used in a completely different context. So there seems to be no more questions. So I would like to ask that would you like to give a message to aspiring undergrads and other people who are pursuing research from your side?
Yeah, of course. I would say that it takes a lot of hard work, a lot of dedication, and everyone always shows you that, like, oh, this worked, this worked, this worked. Let me tell you that the second project, the Chirality one, took over 2 years to get just this crystal structure attempts to grow it. Just trying to get this crystal structure took 2 years, and I didn't give up. So don't give up. You will get there. And when you get there, it'll be one of the biggest achievements. So keep going, and it is worth it in the end. So yeah, just want to say everything takes time and everything takes effort, and just keep pushing.
Thanks for the inspiring message. So since there seems to be no more questions from others, we would close the session. Thank you all for attending, and thank you, Dr. Bismillah, for accepting our invite and coming to this session. It was like really a beautiful talk, and I hope if people have any more questions, then they might contact you in future. So I would request Campus Radio to close the streaming.